In this section, we put things together and present d-separation. As we are presenting it, we can get to d-separation by categorizing paths as active or inactive, which in turn we can do by categorizing the nodes on the path as active or inactive. When are x and y d-separated by z? When there are no active paths between x and y. When is a path active? When all the nodes on the path are active. The concept of d-separation and deconnection are said to be dual. If x and y are d-separated by z, then x and y are not deconnected by z. If x and y are not d-separated by z, then they are deconnected by z. X and y are deconnected if there is any active path between them, and d-separated if there are no active paths between them. Let's work through an example. Are x and y d-separated by the empty set in this graph? To answer the question, we need to look at all the paths from x to y and categorize each as active or inactive. And for each path, we need to categorize the nodes on the path as active or inactive. Let path 1 be the obvious path, x to z2 to y. Is z2 the only node on the path active or inactive relative to the empty set? It's a non-collider, and thus active. So is the path active or inactive? It's active. Is path 2 active? Since z2 is a collider, which is inactive relative to the empty set, the path is inactive. Is path 3 active? Yes. So are x and y d-separated by the empty set, or are they deconnected by the empty set? Because there is at least one active path, they are deconnected. Let's change the conditioning set, but ask the same question. Are x and y d-separated by z1 in this graph? Again, we need to consider all the paths from x to y and categorize each as active or inactive. Is path 1, which was active relative to the empty set, still active relative to the set z1? Since z2 is a non-collider, and since conditioning on z1 does nothing to flip it, the path is still active. Is path 2 active? Now both nodes are inactive, so the path is inactive. Do we even need to look at path 3 to determine the answer to the question? No, we didn't even need to look at path 2. Once we know there is even one active path, we're done. We have deconnection. So are x and y d-separated by the z1? No, they're deconnected. Are x and y d-separated by z2 in this graph? Is path 1, which was active relative to the empty set and the set z1, still active relative to the set z2? Since z2 is a non-collider, and since conditioning on z2 flips it, the path is no longer active. Is path 2 active? Relative to the set z1, both nodes were inactive, so the path was inactive. But relative to z2, z2 is a collider that becomes active, and z1 is a non-collider that we didn't condition on, so it remains active. So the path is now active. Do we even need to look at path 3 to determine the answer to the question? No. We have deconnection. But path 3 is active, and thus x and y are deconnected relative to z2. Are x and y d-separated by the set z1, z2, and z3 in this graph? Yes, as now all three paths are made inactive. Conditioning on z2 deactivates z2 in path 1. Conditioning on z1 deactivates z1 in path 2. And conditioning on z3 deactivates z3 in path 3. It turns out x and y can only be d-separated in this graph by conditioning on z1, z2, and z3. So there you have it. X and y are d-separated by z when there are no active paths between x and y relative to z.